Okay, so you have learned in our first discussion that in circular motion, there are two types of acceleration that we have to deal with. So first of this acceleration is the perpendicular acceleration, which is the acceleration that can cause the change in the object's motion direction. So this is the acceleration that is a requirement for us to have a circular motion. So without this acceleration, the perpendicular acceleration, we cannot have a circular motion. While the other type of acceleration is the parallel acceleration, or the acceleration that is parallel to the velocity of the object. So this is the acceleration that causes the change in speed or causes the change in the magnitude of the velocity. So together with these two accelerations, you can have different types of circular motion. So since there is acceleration, we have a total of two accelerations. That means that we are also dealing with different types of forces. So according to the second Newton's law, whenever there is a force exerted to an object, that would definitely cause an acceleration to that object. And since these accelerations have different directions, that means that the forces that causes each of these accelerations are also different. So for the parallel acceleration, the force that causes this acceleration is a force that is applied parallel to the velocity of the object. Say, for example, this is our moving object here. So at this point, it has a velocity pointing towards that. So that means that if we have a force applied to this object and that force is towards that direction, that means that that force will cause a parallel acceleration, which will cause a change in the speed of this object. So it will speed up. However, if there is a force that is perpendicular to this velocity here, so say for example, the force is applied towards that direction, 90 degrees angle with respect to this velocity, that is the perpendicular force applied. So if that force is applied perpendicularly, then that means that that force can cause a perpendicular acceleration, which is the acceleration that can cause in the change of direction of that motion. So if the force is applied perpendicular to the velocity, it changes the direction of motion, and that is the force that is causing the circular motion, and that force is called the centripetal force. So let's now have a closer look to what this centripetal force is. So a centripetal force is always perpendicular to the instantaneous velocity of the object at any point of the path. So the instantaneous velocity, as you have learned in our previous discussions, is the velocity of the object at any point of the path. Say for example, here we have a video showing you, so for this point here, that is the instantaneous velocity. So that is the direction of the instantaneous velocity. So the centripetal force is accordingly always perpendicular to this instantaneous velocity. So if our object is at this point during this circular motion, at this point, and this is its instantaneous velocity, then this illustration tells us that since the centripetal force is always perpendicular to this instantaneous velocity, then that means that this centripetal force is always pointing towards that direction, towards the center. So we have here another example of a what will happen if we remove the centripetal force. So in the presence of perpendicular force, the object will always turn towards the direction of the force, hence exhibiting the circular path. So without the centripetal force, the object that is moving in the circular path will move out of the circular path and move away. So it will be thrown away from that circular path. Let's see here what will happen if we remove the centripetal force. So in this example, you have a little girl holding a key that is tied into a string, and then she begins to move this key in this circular motion here. And let's see what will happen if she releases that string that is tied to the key. By removing that centripetal force, you can see that the key will be now thrown outwards. And that is the direction of that outward direction of the key is the direction of the instantaneous velocity of that key at that certain point. So you can see that in this circular path, when the key is in that position, the instantaneous velocity is towards that direction, towards the left. And so your centripetal force there is going towards this direction, because again, your instantaneous velocity must always be perpendicular to the centripetal force. When we say perpendicular, that means that the angle between the instantaneous velocity and the centripetal force must equal to 90 degrees. So here is another illustration of that. So we have here the object that is moving towards in a circular path. So this is the original path or the direction of the instantaneous velocity. So this is the circular path here. And so at this moment, the centripetal force pulling the object towards the center is going in that direction. So in this case, you have the instantaneous velocity at this point of the object going towards that direction. So your centripetal force must be going towards that direction. So we can say that at any point of the path, the instantaneous velocity is tangent to the path of motion. By the way, we this motion, I mean this direction here, this direction, and that direction, we call it tangent to the path of the motion. But the centripetal force and consequently the centripetal acceleration, since your centripetal force and centripetal acceleration must have the same directions, both of these quantities must always point towards the center of this circular path, and you have to remember that. So here we have different forces that provide centripetal force. By the way, centripetal force is not a real force, I mean not an actual force that is named centripetal force. Centripetal force is a general term for all the forces that can cause attraction of the object towards the center of the circular path. So we have here four examples, and for examples wherein we have different types of centripetal force. So for this case, we have here a pail filled with water and is attached to a string and then hold upwards by this woman. So it is being pulled towards the center, and then now the pail moves around this circular path. So in this case, the centripetal force is, we call it a tension, because it is the force that exists between an object tied in a string. So here we have another example. The force that is providing centripetal force or attraction of the moon towards the earth is the gravitational force. So the centripetal force for this case is a gravitational force. For the case of a car moving in a curved road, a concrete road, the force that is providing this attraction of the object towards the center of the circular path is this frictional force. While for this object, this say for example, this is a marble that is being rolled in the ground. So we have here a circular path. So the centripetal force in this case is the normal force that is being applied by the ground. So let's have a illustration of these forces. So again, in this case, the centripetal force is the force of tension. In this case, the centripetal force is the gravitational force. In this case, the frictional force is the centripetal force, and here the centripetal force is just the normal force exerted by the ground to the marble. So here again, we have the components of the net acceleration. So we have here the formal names of the parallel and the perpendicular acceleration. So in the previous discussions, I have told you that in our circular motion, we have two types of acceleration, the perpendicular acceleration and the parallel acceleration. This is called perpendicular because it is perpendicular to the direction of the velocity of the object, while the other one is called a parallel acceleration because again it is parallel to the velocity of the object. Now they have formal names. So this one, the perpendicular acceleration, the one that causes the change in the direction of motion, or the one that is a requirement for circular motion, it is called the centripetal acceleration because this is the acceleration that is caused by the centripetal force. On the other hand, the parallel acceleration, the one that is causing the change in speed or the change in the magnitude of your velocity, is known as the tangential acceleration, indicated by E sub tan, and it is just calculated by the usual equation of the acceleration, that is acceleration, or the tangential acceleration, which is the parallel acceleration, is just equal to the change in the velocity over the change in time, or just v sub f, or the final velocity, minus the initial velocity over the time it takes for the velocity to change from the initial velocity to the final velocity. We will discuss later on the equation for the calculation of the centripetal acceleration. But given that we have two different types of acceleration for circular motion, that means that we can calculate, or we have to calculate, for the net acceleration, which is also called the total acceleration. So the net acceleration, or the total acceleration, is just equal to the square root of the sum of the squares of the tangential acceleration, this one, whatever is the result here, you will square that and add it to the square of the centripetal acceleration here, and you get the square root of the total, and that should give you the value of the net acceleration, or the total acceleration. So now let's go to the equations involved in circular motion. How about calculating for the centripetal force? So to calculate for the centripetal force, all you have to do is to use this equation. So your centripetal force, denoted by F sub c, c here is to indicate that this force is the centripetal force, is just equal to the mass of the object times the square of the velocity. So this is the instantaneous velocity of the object, or the velocity of the object at any point during the motion, and then divided by the r, where r is the radius of this circular path. So if this is the center of the circular path and your object is here, then this is the r, or the radius of the circular path. So the centripetal acceleration, which is the acceleration caused by the centripetal force, in that case, all we have to do is to recall F equals ma. This is the equation of the second law of Newton. So the centripetal force is given by this equation, right? So we just copy that, and then we just equate it to the mass of the object times the a, which is the acceleration caused by this centripetal force. Because again, the acceleration, whenever you have an acceleration, that means that there is a force causing that acceleration. So we can do this. And by that, so this one here is equal to this side here, which means that this acceleration here, the centripetal acceleration, can be obtained by just using this equation. So all we have to do is to equate. So we bring the m to the other side of the equation. That means that we can cancel this m here and the m here, because again, we can transfer that to the other side here. M would be placed here in the denominator. So we can cancel out m. So we are left with the square of the velocity divided by the radius. So you can calculate for the centripetal acceleration by getting the square of the velocity. This is the instantaneous velocity here, divided by the radius of the circular path. Now, how about the frequency? So the frequency is the number of revolutions per unit time. Say, for example, you have 10 revolutions, or 10 times that the object repeats the motion. If this is your starting point, and then after 1 seconds, the object have completed 10 rotations, or 10 revolutions around this certain point here. So that means that you have 10 revolutions per 1 second. So you have a frequency of 10 hertz, or 10 per second, which means that you have a total of 10 revolutions per second. So that is your frequency. While you also have the period. So this is the time it takes to complete one revolution, which means that you can calculate for the period by the getting the the time it takes for the object to complete one revolution around this circular path. So say, for example, if the object takes 2 seconds to complete the circular path, if this is the starting point, and then it completes the entire circular path after 2 seconds, then that means that your period is 2 seconds. That is 2 seconds divided by 1 revolution. So that is 2 seconds. So that is just an example. So you can get different frequencies and periods in different scenarios of circular motion. And we also have here the relationship between the frequency and the period. So the period is just equal to 1 over f, or 1 over frequency. So we can say that the period is the inverse of the frequency and vice versa. How about the velocity of the circular motion? So we have talked about here that you can calculate for the centripetal force and the centripetal acceleration using the velocity or the instantaneous of the velocity of the object during this motion. But what if you do not know what is the velocity of the object at any point during this motion? So you can actually recall the equation for the velocity. So velocity is known as the displacement divided by time, or if we are just talking about the magnitude of the velocity, which is the speed, so the speed is just equal to the distance traveled divided by time. Now, for the circular path, or for our circular motion, the distance here traveled by the object, which is the d, is just the circumference of the circle, right? Because again, if you calculate for this total distance traveled by the object from the starting point towards the same endpoint, that is just equal to the circumference of this circular path. So that means that this d here, or this distance here traveled by the object during a circular motion, is just equal to the circumference of the circle, or the circular path traveled by that object. So we just recall the equation for the circumference, that is equal to c. Circumference is represented by big letter C, which is just equal to 2 times pi times the radius of this circular path. Again, the radius is the distance from the center towards this circular path. So now, the time, on the other hand, this one here, is just equal to the period, or the time it takes to complete one revolution. So therefore, given this equation, we can calculate for the velocity of the object during circular motion by doing this. So we just copy this equation, and then we replace distance by the circumference. So this is just d is equal to 2 pi times the radius, and then divided by the time it takes for the object to complete one revolution, that is just equal to the period. So that means that the velocity of the object during the circular path can be calculated by multiplying 2 times the pi times the radius of the circular path divided by the period of the circular motion. And this is how you calculate for the velocity of the object moving in circular motion. Now, given that you already know how to calculate for the velocity, you can calculate for the centripetal acceleration in terms of period, because as you can remember, centripetal acceleration can be calculated using this equation. So all you have to do is to replace the velocity here by this equation, because again, the velocity is just equal to this, right? So the velocity will be replaced by this. So the centripetal acceleration is just equal to 2 pi r divided by the period, that should be squared, over the radius of this circular path. And so given that you have this, so if you square 2, that should be 4. Square of pi, that is pi squared, and square of r is just r to the 2. And then we divide it with the square of the period, that is t to the 2, and then you have here another r term for the denominator, this one. So you can cancel out 1r here and another r here at in the numerator. So that means that you can actually calculate for the centripetal acceleration using this equation. So you have now two equations, or two possible equations to calculate for the centripetal acceleration. You can calculate the centripetal acceleration using this equation or using this equation. So you just choose between these two equations, whichever is available in the given. Now, we have different types of circular motion. So the circular motion is categorized into two types. We have the uniform circular motion, and we also have non-uniform circular motion. What is the difference between these two? So in uniform circular motion, we can say that the object is moving in uniform circular motion only if the centripetal acceleration that keeps the object moving around the circle is acting on the object. In other words, we can say that the object in uniform circular motion if the speed of the object moving along the circular path is constant, which means that you should not have a tangential acceleration. So your acceleration here is only one. So, di ba, we have two types of acceleration. We have centripetal acceleration, the one that is perpendicular to the velocity, and we also have the tangential acceleration, which is parallel to the velocity. So if your tangential acceleration is equal to zero, that means that you have a uniform circular motion. The object is still moving around a circular motion because of the presence of the centripetal acceleration. But since your tangential acceleration is equal to zero, the velocity of this object moving around the circular path must be constant. So your velocity here is constant. Now, in the non-uniform circular motion, there are centripetal acceleration as well as tangential acceleration acting on the object. So, in the non-uniform circular motion, both of the accelerations mentioned a while ago are present. So, your object is moving in the circular path, then at the same time, its velocity is increasing because of the tangential acceleration, or its velocity is decreasing because of negative tangential acceleration. So here in the non-uniform circular motion, there are centripetal acceleration and tangential acceleration and acting on an object. In other words, the speed of the object changes, or its velocity, the magnitude of its velocity, the speed of the object is changing while it is moving around a circular track. So in our different cases of circular motion discussed in the previous slide, di ba, we have constant speed, increasing speed while following a curved path, and we also have decreasing speed while following a curved path. We can actually label them according to what type of circular motion they are. So in our case A, when the speed is constant along a curved path, that means that this one here, this case, is a uniform circular motion. However, in our case B, when the speed is increasing along the curved path, we have a non-uniform circular motion with positive tangential acceleration. This acceleration here must be positive because this object is speeding up. While in case C, when the speed is decreasing along a curved path, this is another non-uniform circular motion with um, negative tangential acceleration because again, the object here is decelerating or its speed is decreasing. So I hope that is now clear to you. And here we have an example problem. So a 1,000 kilogram car accelerates from rest to a speed of 40 meters per second in 10 seconds. So meaning we have here an acceleration and it is following a circular path or a circular track with a radius of this. So the questions are what is the tangential acceleration, what is the centripetal acceleration, and what is the net acceleration. So remember that the tangential acceleration is the acceleration that causes the change in speed, which means that we can calculate for this tangential acceleration using this information here from rest and then speeds up to 40 meters per second in 10 seconds. And then remember that the centripetal acceleration is the acceleration that causes this object to follow a circular path. That is the acceleration that causes the change in its direction. And the net acceleration is the total of these two accelerations. Okay? So now let's go to the calculations. So to solve for the tangential acceleration, which is the acceleration that causes the change in velocity, all we have to do is use the usual equation for the calculation of acceleration. So the tangential acceleration is just the change in velocity per unit of time, which means that we have here the final velocity minus the initial velocity divided by the time it takes for this change in velocity. So we have 40 meters per second minus 0 because our initial velocity here is at rest or that means that the initial velocity is equal to 0, right? So divided by the 10 seconds, which is the time it takes for this car to accelerate from 0 to 40 meters per second. So that should give us 4 meters per second squared tangential acceleration. Now to solve for the centripetal acceleration, all we have to do is to use our equation before described in the previous slide here. So this is how we calculate for the centripetal acceleration. So our centripetal acceleration is just equal to the velocity of the car during this moment, that is 40 meters per second, divided by the radius of the circular path. So the radius of the circular path is 500 meters, so that is 40 meters per second squared divided by 500 meters radius, and that should give us 3.2 meters per second squared. So that is our centripetal acceleration. Now to solve for the net acceleration, or also called the total acceleration, all we have to do is to use this equation here, because again we can think of the tangential acceleration and centripetal acceleration as the x and the y components of your total acceleration. So our net acceleration is just equal to the square root of the sum of the squares of the tangential acceleration and the centripetal acceleration. So your tangential acceleration here is 4 meters per second squared, and then we square it and add the square of the 3.2 meters per second squared, and that should give us a total or net acceleration of 5.12 meters per second squared. And that's how you solve problems involved in circular motion. So there is also an important note to have a difference between that we have difference between circular motion and rotational motion. So the most clear or the most obvious example here of these different cases is the revolution and the rotation. So the revolution is an example of a circular motion. This refers to the object's orbital motion, or motion around another object, or movement around an external point associated with an orbit. So say for example here, the motion of the Earth around the Sun, that is an example of a circular motion, or approximately circular motion, and that is a revolution. However, rotational motion is different in a matter of fact that it refers to an object's motion or spinning motion about its own axis, which means that the object is moving around an internal axis, or the point where the object moves is just inside of its body. And this is associated with a spin. Say, for example, the rotation of the Earth around its own axis is what we call a rotation. So these are examples of rotational motion here. The movement of a wheel, this one, the propeller, and the rotation of a top. So these are rotational motion, while circular motion is the motion of the Earth around the sun. So that is the difference between circular motion and rotational motion. And aside from that, the equations involved in rotational motion are different from the equations used in circular motion, because here we will be dealing with the angular displacement, unlike in the circular motion, we are still using here, as you can notice, we are still using these terms or these quantities, while in the rotational motion we will be dealing with the change in the angles or the angular displacement. So I hope that helps, and later we will have another topic to discuss. Thank you very much and have a great day.